Hello everyone, this is Mix K. Today I'm going to be talking a little bit about the types of bonds. So recently we've been talking a lot about valence electrons and how our atoms want to have 8 valence electrons. Now, having 8 valence electrons is called an octet, a full octet. And when our atoms already have a full octet, when they already have 8 valence electrons, all those electrons are paired up. The atom is stable, it does not want to change, and the atom no longer bonds. If an atom does not have 8 valence electrons, it does not have a full octet, it's going to try and bond until it can get a full octet. Now, I want to talk to you guys about this term called electronegativity. Electronegativity is an atom's ability to attract electrons. It's how good an atom is at getting the electrons it needs. Now, when we look at the periodic table, our nonmetals, which are these ones I've circled in red over here, our nonmetals tend to have higher number of valence electrons. They're closer to having 8. So nonmetals tend to have high electronegativities. They're really good at attracting those last couple electrons they need to get 8. They really want just 1 or 2 or 3 more electrons to fill up their octet. So they have high electronegativities. They're good at attracting electrons. This is kind of like when you are saving up for something, a new game, some new clothes, whatever you're looking to save up for. And you only need like $20 to be able to buy the thing you want to buy. You're going to do whatever you can to get that last $20. You really want it. These atoms are the same. They're so close to getting their goal of 8 valence electrons, that magic number, that they're going to work really hard to get 8. They're going to have high electronegativities. Metals, on the other hand, tend to have low numbers of valence electrons, only like 1 or 2 or 3. So they actually have low electronegativities. They're not good at attracting electrons. They're so far away from having 8, they're just like, you know what? I'm going to get rid of these last couple electrons and drop down to my next lowest 8. They have 8 more underneath that. So they're like, yeah, take my couple extra electrons. I don't need them. I have 8 more underneath. So metals have low electronegativities. They're bad at attracting the electrons. They actually just give them away. Okay, so metals and nonmetals are going to try and get 8 valence electrons. Metals have low number of valence electrons, so they just lose those electrons and drop down to 8. They have low electronegativities. Nonmetals are really close to having 8. So they're either going to gain or share their electrons to fill up to 8 valence. No matter what, we end up with 8. But metals that have low electronegativities are going to lose their electrons to drop down to 8. Nonmetals that have high electronegativities are going to gain or share electrons to fill up to 8. So nonmetals are better at attracting electrons than metals. Nonmetals have high electronegativities. They're better at attracting electrons. Now, I want you to think about this little story for a minute to help you remember the types of bonds. So we're going to have a little tug-of-war competition. So our first tug-of-war competition is between 2 twin bodybuilders. Now, when these bodybuilders go to do their tug-of-war, they're both just as strong as each other. So when they go to pull on that rope's not going to go anywhere. It's going to be stuck right in the middle because they're both pulling with the same strength. This is kind of like a non-polar bond. In a non-polar bond, you have 2 non-metal atoms, and they both have high electronegativities. You can think about them as being stronger. And so both those nonmetals are going to pull on our electrons. We're going to imagine the rope is our electrons. And because they both really want those electrons, they're both going to pull with the same strength. And those electrons aren't going to go anywhere. They're just going to hang out in between the 2 atoms. So two nonmetal atoms with the same strength, they're both really strong, they both really, really, really want those electrons, are going to pull on them with the same strength, and because of that, they're going to have to share them equally. They're not going to go anywhere. Another type of bond would be like a bodybuilder versus a strong guy. Now, this guy works out, but he's not quite as strong as the bodybuilder. So when that bodybuilder goes to pull on that rope, he's going to be able to pull it closer to him because he's stronger, but this other guy is not going to let go. He's not going to win, but he's not going to let go of that rope. This is kind of like a polar bond. In a polar bond, we still have two nonmetals, so they're both really strong. They both have high electronegativities. But one of those nonmetals has a slightly higher electronegativity. It's a little bit better at attracting electrons. So it's going to pull those electrons towards it, pull a little bit closer. Now, the other atom isn't going to let go. It still needs those electrons. So they're going to have to share them, but they're going to share them unequally. So these are both examples of covalent bonds. Covalent bonds are made of just nonmetal atoms. A nonpolar covalent bond is when both atoms have very similar electronegativities. They're both going to share those electrons equally. So here, this blue area is showing that the electrons are spread out evenly around those two atoms. In a polar bond, though, one of those atoms is a little bit stronger and pulls the electrons over to its side. Now, when this happens, we get what's called partial charges. They're not full charges, they're just partial. That's what this little symbol represents. So when one atom pulls the electrons closer to its side, it makes it a little bit negative. And because the electrons are pulled away from this other atom, it makes it a little bit positive. So polar means a separation of charges. Kind of like the North and South Pole are on separate ends of the Earth and its magnetic field. Here we have two charges on either end of the bond that are partial. They're kind of negative and kind of positive. Nonpolar, no charge, they share equally. Polar, we have a separation of charges because they share unequally. Now, our last type of bond, we're going to look at an example where we have a bodybuilder versus a baby. Now, when this bodybuilder goes to pull on that rope's just going to come right out of that baby's hands. That baby's not holding on to the rope. He's just kind of like, blah, 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 I'm a baby. Take the rope. I don't care. And so that bodybuilder is going to be able to pull the whole rope over to his side. This is kind of like an ionic bond. In an ionic bond, you have a nonmetal that is much stronger. It has a much higher electronegativity. And you have a metal that has a really low electronegativity. It's much weaker. So that nonmetal just takes the electrons from the metal. And this ends up having us have an ionic bond. Now, if we look at atoms here, this metal has just one extra electron in its outer ring. And this nonmetal has 7. So what's going to happen is this nonmetal has a higher electronegativity, it has a higher strength, and it's going to take that electron from the metal, which is weaker. But if we look at their outer rings now, the nonmetal has gained 1, it has 8. And when that metal lost 1, it dropped down to its next lowest ring, and it has 8 there as well. So what's really nice about this interaction is they both still end up with 8. It's just the nonmetal fills up to get 8, and the metal drops down to get 8. Now, what holds these atoms together? When this nonmetal gains an electron, it gets a negative charge. And when this metal loses an electron, it gets a positive charge. So when there's a positive plus a negative, they attract and stick together like magnets. So those opposite charges attract, and that's what holds our atoms together. In a covalent bond, though, what's holding the atoms together is they're sharing their electrons. Neither of them wants to let go of those electrons, so they're stuck together. Now, there's one more type of bond I want to talk about, and that's a metallic bond. In a metallic bond, we have just metal atoms. And what happens with their electrons is that their electron clouds overlap a lot. And so those electrons can move freely from one atom to another. It's kind of like a sea of electrons surrounding those nuclei. Think about a pool filled with people. The people would be the atoms, and the water would be the electron cloud. That water can flow through the pool. It can move from person to person. It's not just attached to one person. So here we can see that the electrons can move freely throughout that metal. This is why metals are good at conducting electricity. Because there's already electrons flowing through, if I add some extra electrons, they can move through the metal and come out the other end. This is also why metals are really good at being bent and shaped. If I start hammering down on the top of this metal, those atoms are going to actually just get shoved down into those bottom layers. So if I keep hammering on it, the layer is going to spread out thin with those atoms just getting smushed down into the bottom layers. So metallic bonds are just metal atoms. Now I'm going to switch over here to the practice where I actually show you how you can find the type of bonds. And the only thing I need you to copy down into your notes is this little cheat sheet here. Okay. Now we have two methods to find our type of bond. The first method is we just look at the element types. So let's start there. So here I have carbon and hydrogen. I'm going to go look at my little periodic table and I outline the ones that are nonmetals in red. So carbon is a nonmetal and hydrogen is a nonmetal. They're both nonmetals. So when I have two nonmetal atoms, that is going to be a covalent bond. Nonmetal plus nonmetal is covalent. Now, the other way I can find the type of bonds gets me a little bit more information. Now, one thing real quick, guys, I did make a typo on these slides. So if your slide doesn't say 1.7, it should right here. But it also has it correct on this top slide. So if you look here, it says 1.7. I just made a little typo and wrote the wrong number right here. Okay, anyway, to find the type of bond using electronegativity, we're going to look at the difference. So the difference in these electronegativity values. The difference in how strong they are, how good they are at attracting electrons. So remember, difference means subtract. So we're going to look up those two elements and subtract their electronegativities. If their electronegativity difference, the difference in their electronegativities is really small, 0.0 to 0.4, that's kind of like our twin bodybuilders. They're going to share their electrons equally, so it's going to be non-polar. Now, if the difference is a little bit bigger, that means one atom's a little bit stronger than the other. That means they're going to share them unequally, and it's going to be a polar covalent bond. And then if the difference is really, really large, one atom is much stronger than the other, then we're going to have the nonmetal taking the electrons from the metal, and that means we have an ionic bond. Okay, so this gets us a little bit more detail. The first method, a little quick, is it covalent, is it ionic? Here we're finding out if it's polar or non-polar or just ionic again. So I'm going to look up carbon and hydrogen for my example. So I have carbon is 2.5, hydrogen is 2.1. So I'm going to type that in, 2.5, 2.1, and then I subtract. I'm always going to do the big number minus the small number. You should never get a negative number for this. If you do, just make it positive. Then I need to check my chart. So if I look up here, I got 0.4. So I want to see which of these ranges does my difference fall into. So I got 0.4, so that falls into 0.0 to 0.4. So it's got to be non-polar covalent. So all I have to do is subtract and then check the chart. Okay. Let's try another one. So here I have H and O. So first I'm going to look up if they're metals or non-metals. So hydrogen is a non-metal. Oxygen is a non-metal. So I have non-metal plus non-metal is covalent. Non-metal plus non-metal equals covalent. Now to get a little bit more detail, I'm going to do the electronegativities. There's my typo. Okay, so I'm going to go look those up. H is 2.1. O is 3.5. So I'm going to put that in. 2.1, 3.5. And then I'm going to subtract big minus small. 3.5 minus 2.1 equals 1.4. So I'm going to go check my table. So nonpolar is 0.0 to 0.4, so it's not going to be that one. But 1.4 does fall in between 0.5 and 1.6. So this has to be a polar covalent bond. It falls into this range, so it's going to be polar covalent. Okay, let's try another one. So I have Na and Cl. So first let me look up what types of elements they are. So Na is a metal. It does not have that red outline in that section. Chlorine is a non-metal, so I'm going to type that in. I have a metal and a non-metal. So metal plus a non-metal is going to be ionic. Now, if I get ionic here, I should get ionic over here. If I get covalent over here, I should get polar or non-polar over here. There are a couple exceptions, and I'll show you one later on, but they should match up. If you're getting like non-polar and ionic, you know you made a little bit of a mistake. So now let's look up the electronegativities. So I have Na is 0.9, Cl is 3.0. So I have 0.9, 3.0, and I'm going to subtract big minus small. 3.0 minus 0.9, and I have a difference in electronegativity of 2.1. So this falls in between 1.7, that's a typo, 1.7 and 3.3, so this is going to be ionic. So this one had a really big difference in electronegativity, so it's an ionic bond. Pause the video here. Try these next two examples. Okay, so pause, and then in a minute you can unpause, okay? So pause, okay, unpause, and here we go. So we have oxygen, so we're looking at the bond in between oxygen atoms. So I'm going to come up to my chart and I look up oxygen as a non-metal. And while I'm here, I'm going to grab the electronegativity is 3.5. So here I have two non-metals, non-metal plus a non-metal, so it's going to be covalent. My electronegativity was 3.5, but they're both oxygen, so they both have the same electronegativity. So when I go to subtract, I'm going to get 0. Okay, non-polar is 0.0 to 0.4, so this is going to be a non-polar covalent bond. Okay, one more example. So here we have MgBr2, magnesium bromide. So I'm going to look up magnesium and bromine on my periodic table. Okay, magnesium is a metal, and bromine is a non-metal. So I have a metal and a non-metal. If I have a metal plus a non-metal, it's going to be ionic. Sorry. Now let's do our electronegativities. So if I go look at my chart, magnesium has an electronegativity of 1.3. Bromines is 2.8. So I have 1.3. I have 2.8. I'm going to subtract. Now, this is one of those exceptions I was telling you about. When I subtract, I get 1.5. So this should tell me that it's polar. And if you told me polar here, I wouldn't take points off because that's what it's technically telling you on the chart. But this is actually, wait, I can't spell, actually ionic. Because it is a metal and a non-metal, it's going to be ionic. Maybe this doesn't have as strong of an ionic character as maybe some of our other ones do, but because it's a metal and a non-metal, it's going to be ionic. Occasionally, you'll get ionic over here and polar over here, but it's still going to be an ionic bond, okay? If you said polar, I wouldn't take off points, but if you did say ionic, you would still get points as well. I'm going to try and not give you ones that are weird like this when we have like quizzes and stuff, but I did want to let you know in case I make a mistake and give you one of these weird ones that if you do get something a little bit smaller, but it's still a metal and a non-metal, it's going to be ionic. Okay, so there is some homework, there is some extra credit. Feel free to rewatch this video if you need to look over those examples again. And I hope this helped. Have a lovely day, everybody.